Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be drifting through the magnificent forces of nature, the hidden machinery of the universe, and the deep laws that guide every movement in the cosmos. These forces are as ancient as creation itself, and equally as mysterious. All around you, unseen powers are at work, quiet, relentless, and everywhere at once. They bind the stars, hold the atoms, and choreograph the motion of galaxies and dust alike. You can't see them, but you can feel their pull in every moment. They are the silent sculptors of reality, the reason the universe holds together instead of flying apart. From the gentle tug that keeps your feet on the ground, to the cosmic threads that shape time and space themselves, these forces connect everything that has ever existed. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Allow your breathing to slow and your mind to grow still. Let's begin. Gravity is so weak you can overcome it just by lifting your hand. Gravity feels strong because it keeps oceans from drifting into the sky and holds the moon in orbit around Earth. But compared to the other forces of nature, it is astonishingly weak. You can defeat the gravitational pull of an entire planet simply by raising your arm. The electrical forces in your muscles are trillions of times stronger. Yet gravity's influence stretches across the universe because it never cancels out. Every bit of mass attracts every other. That means every planet, star, and galaxy adds its pull to the cosmic total, forming an invisible web of connection. This quiet persistence is what lets gravity dominate the universe at large scales. It's the paradox of existence. The weakest force is also the one that holds everything together. A whisper of attraction, barely noticeable, binding reality from the smallest grain of sand to the grandest cluster of galaxies. Yet it binds galaxies together across billions of light years. If you could stand outside the Milky Way and watch it turn, you'd see hundreds of billions of stars circling an unseen center, held in place by gravity's patient hand. Every star you see moves along the curved fabric of space-time carved by the galaxy's mass. And around that, dark matter, invisible yet vast, deepens the gravitational well, anchoring everything together. Even neighboring galaxies feel the same pull. Over billions of years, they drift toward each other, merging in slow-motion dances that can take entire cosmic ages to complete. The same process repeats on even larger scales. Galaxies group into clusters, clusters form filaments, and those filaments weave the architecture of the observable universe. All of it held in balance by the same simple law that keeps an apple falling toward Earth. The weakest force in physics is also the strongest sculptor of the cosmos. Every atom in your body bends space-time. Even you warp the universe. It's easy to imagine gravity as something that only belongs to planets and stars. But Einstein's equations say otherwise. Everything with mass, everything that exists, bends space-time, no matter how small. You do it right now. Your body slightly alters the paths of photons passing by. The chair you're sitting on curves space-time too, as do the walls, the air, and even the microscopic dust floating around you. These distortions are unimaginably tiny, but they're real. They ripple outward forever, faint signatures of your presence written into the structure of the cosmos. In a sense, gravity is not something you feel, it's something you create. You are part of the same fabric that binds galaxies and pulls moons through the dark. Space itself reshapes to accommodate your existence, proof that every living thing leaves its imprint on the universe simply by being. Light can be curved by gravity, making the cosmos act like a lens. When light passes near something massive, it follows the curvature of space-time. It doesn't change direction because of a pull, it simply moves along the geometry of reality itself. This effect is called gravitational lensing, and it lets us see farther than would otherwise be possible. Massive galaxies bend light from even more distant ones, creating rings, arcs, and ghostly duplicates of entire galaxies billions of light-years away. Through these natural cosmic lenses, astronomers can peer deep into the early universe, observing light that has traveled for nearly its entire history. Sometimes, a single beam of light can loop around a galaxy more than once before reaching us, arriving from multiple directions at once. Gravity turns the entire cosmos into a living telescope, allowing space to magnify its own secrets. Even light, the fastest thing in existence, must bow to gravity's shape. Gravitational waves are ripples in space-time that stretch reality itself. Imagine the universe as a vast ocean of space-time. When massive objects move, they send out waves that ripple across this cosmic sea. These are gravitational waves, vibrations of the universe's very fabric. When two black holes orbit each other, or when neutron stars collide, they make space-time quiver, stretching and squeezing everything in their path. The effect is unimaginably small, less than 1,000th the width of a proton, yet scientists have built detectors sensitive enough to feel it. In 2015, the Laser Interferometer Gravitational Wave Observatory recorded such a signal for the first time, a faint chirp from two merging black holes over 1 billion light-years away. It confirmed Einstein's prediction a century after he made it. Space and time, it turns out, are not fixed and silent. They can ring like a bell, and the universe is full of echoes. Two colliding black holes can release more energy than every star combined. When two black holes spiral into each other, they unleash one of the most powerful events known to physics. In a fraction of a second, they can radiate more energy than every star shining in the observable universe, not as light, but as gravitational waves. Each black hole bends space-time so extremely that, as they merge, the curvature snaps and shakes reality itself. The energy released doesn't come from anything being burned or exploded. It's drawn from their motion, their rotation, and the collapsing geometry of space. What's left behind is a single, larger black hole, calmer, smoother, and darker than before. The collision ends in absolute silence, but its ripples race outward through the cosmos, carrying the memory of that moment forever. It's proof that even in darkness, the universe finds a way to sing through the language of gravity. Gravity moves at the speed of light, not instantly as once believed. For centuries, gravity was imagined as an invisible tether, acting instantaneously across distance. If the sun vanished, Newton's laws implied Earth would feel it immediately. But Einstein's relativity changed everything. It showed that gravity isn't a pull transmitted through space. It is space itself responding to mass, and that response moves no faster than light. When the sun's position changes, Earth feels the new curvature of space-time about 8 minutes later, the same time sunlight takes to reach us. This revelation unites gravity with the rest of physics, tying it to the same cosmic speed limit. It also keeps the universe stable, preventing impossible cause and effect paradoxes. When black holes collide or stars shift, their gravitational influence ripples outward at light speed, announcing change through vibration, not force. Gravity isn't instant. It's the geometry of the universe updating, one wavefront at a time. Time slows down in stronger gravity. Your head literally ages faster than your feet. Einstein discovered that gravity doesn't just bend space, it bends time. The stronger the gravitational field, the slower time flows. On Earth, this difference is measurable. Atomic clocks placed at different heights tick at slightly different speeds. A clock on a mountaintop runs faster than one in a basement. Even your own body experiences a faint gradient. Your head, farther from Earth's center, ages a few nanoseconds faster than your feet each year. It's a tiny effect, but one that GPS satellites must account for to stay accurate. Near a black hole, this distortion becomes extreme. Seconds can stretch into centuries. Gravity turns time into a flexible dimension, slowing it where mass is dense and stretching it where space is open. Every tick of every clock in the universe is tuned not to some universal rhythm, but to the local curvature of space-time. Earth's gravity isn't uniform. It's weaker over oceans and stronger over mountains. We think of gravity as constant, but the Earth's gravitational field is subtly uneven. It changes with density, elevation, and the shifting motion of magma and water beneath the surface. Mountains, dense rock, and crustal plates create stronger local pull, while deep ocean basins, glaciers, and molten regions have slightly weaker gravity. These tiny variations, often just a few millionths of a G, can be mapped by satellites orbiting Earth. The resulting models reveal hidden structures beneath continents, track the melting of polar ice, and even monitor groundwater changes across regions. The shape that defines these differences is called the geoid, the true wobbly shape of Earth's gravity field. Though we never feel it, our weight and the pull beneath our feet change as the planet breathes, melts, and drifts. Gravity, ever patient, responds to every shift within the living world. Astronauts float not because there's no gravity, but because they're falling forever around Earth. Weightlessness isn't the absence of gravity, it's the experience of falling. Astronauts aboard the International Space Station are only a few hundred kilometers above the surface, where Earth's gravity is almost as strong as on the ground. They float because they're in perpetual freefall. The station is moving forward at nearly 8 kilometers per second. As it falls toward Earth, the ground curves away at the same rate, creating an endless descent that never reaches the surface. Everything inside the spacecraft, astronauts, tools, droplets of water, falls together, eliminating the sensation of weight. This delicate balance between velocity and gravity is what defines an orbit. Its motion turned into equilibrium, falling turned into flight. Each circuit around the planet is a quiet conversation between speed and pull, proof that even in space, gravity never lets go. It only changes shape. A single photon has no mass, yet it can push on a solar sail in space. Light carries no rest mass, yet it possesses momentum, the ability to push against matter. When photons strike a reflective surface, they transfer an almost imperceptible pressure called radiation pressure. In space, where there is no air to resist motion, this gentle push becomes a true form of propulsion. Solar sails are vast, mirror-like sheets designed to catch this pressure and convert it into motion. The Japanese spacecraft Ikaros proved that sunlight alone can accelerate a ship through space. Every second, billions of photons bounce off the sail, nudging it forward with endless patience. Over time, this adds up, allowing travel without fuel, noise, or engines. Future interstellar missions may use lasers to drive sails to incredible speeds, crossing the gap between stars in decades rather than millennia. Light, the purest form of energy, can move worlds without ever touching them. Every spark, magnet, and light beam comes from one force: electromagnetism. Electricity, magnetism, and light are not separate things. They are different faces of a single, unified force: electromagnetism. James Clerk Maxwell discovered this connection in the 19th century when he realized that changing electric fields create magnetic fields, and changing magnetic fields create electric ones. Together they form electromagnetic waves that travel through space at the speed of light. The glow of a star, the hum of a power line, the spark of lightning, and the invisible waves carrying your voice across the planet are all born from the same interaction. It is electromagnetism that allows atoms to hold together, molecules to form, and energy to travel freely across the cosmos. Every sight you see and every sound you hear exists because of this one force, endlessly weaving energy through space in the form of light. Electric and magnetic fields are two sides of the same invisible fabric. For centuries, electricity and magnetism seemed unrelated. One made sparks leap, the other turned compass needles toward north. Then scientists discovered that they were inseparable parts of a single entity, the electromagnetic field. Move an electric charge and a magnetic field appears. Change a magnetic field and an electric current flows. This constant exchange is what keeps energy moving through the universe. It is why light exists and why radio waves can travel through the vacuum of space. Even in complete darkness, the electromagnetic field is never still. It shimmers with quantum energy, alive with particles appearing and disappearing too quickly to see. Everything from sunlight to X-rays is simply a different vibration of this one field, rippling through the emptiness. Electricity and magnetism are not opposites. They are partners, forever intertwined in the structure of reality. Without electromagnetism, atoms would instantly fall apart. At the heart of every atom, a nucleus of protons and neutrons sits surrounded by a cloud of electrons. The only reason those electrons stay nearby is electromagnetism. The negatively charged electrons are drawn toward the positively charged nucleus, creating balance. Without that attraction, electrons would drift away and matter itself would dissolve. At the same time, the electric repulsion between protons and the nucleus would tear atoms apart, if not countered by the strong nuclear force. Together, these two forces form the foundation of everything solid. The walls around you, the air you breathe, your own body, all exist because electromagnetism binds matter into stable form. It holds the chemical bonds that make molecules, and it governs the light that allows you to see them. Without it, the universe would be nothing but an invisible cloud of unbound particles. The same force that powers stars also runs through your brain's neurons. The electric signals that flash through your brain are the same fundamental phenomenon that powers the stars. Both arise from electromagnetism. In your neurons, tiny electrical charges travel along membranes, triggering the release of chemical messengers that create thought, memory, and movement. In stars, similar charges govern the flow of plasma and control the fusion reactions that produce light and heat. The difference is scale, not principle. Both rely on the same laws of attraction and repulsion, the same currents and fields, the same universal equations. When you think, when your heart beats, when you see light from the sun, it is electromagnetism at work in two vastly different arenas of nature. The same force that builds galaxies also whispers inside your mind. Lightning is a 50,000-degree river of plasma connecting cloud and ground. A lightning bolt begins when electric charges build up in storm clouds until the air itself can no longer resist. Suddenly, a channel of plasma bursts into existence, connecting the cloud to the ground in a brilliant flash of light and sound. The temperature can soar above 50,000 degrees Celsius, hotter than the surface of the sun. Each bolt lasts only milliseconds, yet it carries enough energy to power a city block. What you see as a single strike is often a rapid series of discharges flickering along the same path. The sound of thunder is the air itself expanding explosively from that heat. Lightning is one of Earth's most dramatic demonstrations of electromagnetism, a raw reminder that electricity isn't just a human invention. It's a natural force that shapes the atmosphere and balances the planet's electrical heartbeat. The northern lights are Earth's magnetic field made visible. When charged particles from the sun reach Earth, they are guided by our planet's magnetic field toward the poles. There they collide with atoms in the upper atmosphere, causing the air to glow in shimmering curtains of green, pink, and violet light. These are the auroras, nature's magnetic artwork. Each color represents a different gas reacting to the incoming energy, oxygen producing green and red, nitrogen creating purples and blues. The display ripples and moves as magnetic lines shift under the pressure of the solar wind. Sometimes the entire sky seems alive, flickering like a slow cosmic heartbeat. The auroras remind us that our world is surrounded by invisible fields, constantly interacting with the storms of the sun. Without this magnetic shield, those same particles would strip away our atmosphere. Beauty, in this case, is also protection. Magnetic fields stretch across entire galaxies. Magnetism doesn't stop at the scale of planets or stars. It extends across the vast reaches of interstellar space. Within galaxies, magnetic fields thread through clouds of gas and dust, influencing how stars are born and how cosmic rays travel. These fields are faint, far weaker than the magnetism of a refrigerator magnet, yet they span tens of thousands of light years. Astronomers map them using polarized light and radio waves, tracing the subtle ways they twist and align across the spiral arms of galaxies. Even between galaxies, magnetic fields stretch across the empty void, linking clusters into larger structures. No one yet knows how these immense magnetic webs first formed, but they shape the motion of matter on cosmic scales. Magnetism, which guides a compass needle on Earth, also helps steer the evolution of the universe. The sun's magnetic field flips direction every 11 years. Our star has a magnetic heartbeat. Roughly every 11 years, the sun's magnetic field reverses its polarity, flipping north and south. This cycle drives the rise and fall of sunspots, solar flares, and massive ejections of plasma into space. During the peak of solar activity, the sun's surface boils with magnetic storms, its energy twisting and snapping magnetic lines like rubber bands. Eventually, the field reorganizes, calm returns, and the cycle begins anew. These magnetic fluctuations affect everything from satellite operations to Earth's auroras. They even influence the solar wind, the stream of charged particles that fills the entire solar system. The sun is not just a ball of fire, it's a living magnet whose field stretches past the orbit of Pluto. Every few years, it quite literally turns itself inside out. All chemical reactions, colors, and sounds come from electromagnetic interactions. The world of sensation is built on one force, electromagnetism. The colors you see are specific wavelengths of light absorbed and reflected by electrons in atoms. The sounds you hear are vibrations converted into electrical signals inside your nervous system. The texture of a surface, the scent of the air, the warmth of sunlight on your skin. All of it comes down to electromagnetic forces acting between particles. When molecules react, it's because electrons are trading partners or rearranging their orbits. When you touch something solid, it's electromagnetism that keeps your hand from passing through it. Even fire is an electromagnetic phenomenon, light emitted as atoms release energy. Every experience you've ever had, every sensation of beauty or warmth or color, is a conversation between your body and the electromagnetic field that fills the universe. The strong nuclear force is so powerful it could lift 1 trillion tons in a teaspoon. The strong nuclear force binds protons and neutrons inside the atomic nucleus. It is the mightiest force known, about 100 times stronger than the electromagnetic force and vastly stronger than gravity. If it could be harnessed on a macroscopic scale, a single teaspoon of strong force energy could lift entire mountain ranges. This strength comes from particles called gluons, which act as the glue holding quarks together. The strong force only acts over incredibly short distances, less than 1 trillionth of a meter, but within that range it dominates everything. It's the force that powers the sun through nuclear fusion and gives all ordinary matter its stability. Without it, atoms would disintegrate and the universe would dissolve into a thin mist of radiation. The strong force is nature's unbreakable bond, the hidden tension inside everything solid and real. It's the only force that grows stronger when you try to pull it apart. Most forces weaken with distance, but the strong nuclear force behaves in the opposite way. When quarks inside a proton are close together, the force between them is gentle. Try to separate them, and it tightens like a stretching elastic band. Pull harder, and the energy becomes so great that new quark pairs pop into existence instead of letting the originals escape. This phenomenon is called confinement, and it means that no one has ever observed a single quark in isolation. The more you try to free one, the more the universe resists. It's as if nature has decided that the building blocks of matter must always remain together. This counterintuitive property keeps atoms stable, prevents the nucleus from falling apart, and ensures that matter, once formed, stays bound. The strong force is the ultimate lesson in togetherness. Almost all your mass comes from the energy of this invisible binding. Protons and neutrons are made of quarks, held together by the strong nuclear force. But if you added up the mass of those quarks, it would account for only a tiny fraction of the total. The rest comes from energy. According to Einstein's equation, E equals mc2, energy and mass are two forms of the same thing. Inside the nucleus, quarks and gluons move at near light speed, generating enormous kinetic and binding energy. That energy manifests as mass. In other words, most of what gives you weight, what makes your body tangible, is energy trapped inside atomic nuclei. You are built not from solid matter, but from the restless motion of particles bound by invisible tension. The strength that holds the universe together is literally what makes you exist. Inside every proton, particles blink in and out of existence constantly. A proton seems simple, but it is a storm of activity. 3 quarks form its core, yet countless virtual particles appear and vanish inside it every moment. Gluons exchange between quarks, splitting and recombining in an endless dance of energy. Quark-antiquark pairs emerge from the vacuum, exist for an instant, and disappear again. This internal chaos is what gives the proton its mass and stability. Far from being a solid sphere, it's a seething, dynamic cloud of fields and forces, balanced so precisely that it endures for billions of years. The same quantum turbulence fills every nucleus in your body. Matter, on the smallest scale, is never still. It is a continuous flicker of creation and destruction, an ocean of energy wrapped inside the calm surface of the everyday world. The sun shines because the strong force releases energy through fusion. Deep inside the sun, gravity compresses hydrogen atoms until their nuclei are forced close enough to fuse. The strong nuclear force takes over, binding them together into helium and releasing energy in the process. That released energy becomes sunlight, heat, and the radiation that sustains life on Earth. Every second, The Sun fuses about 600 million tons of hydrogen, converting a small portion of that mass into pure energy. The process is a delicate balance between gravity's inward pull and the strong forces binding power. Fusion is not just a stellar process, it is the heartbeat of the cosmos. Every star in the night sky shines for the same reason, each one a living demonstration of how strength and balance create beauty. The weak force lets neutrons decay, creating the elements of life. The weak nuclear force allows certain particles to transform into others, turning neutrons into protons, electrons, and neutrinos. Without this process, called beta decay, the universe would be frozen in its earliest state of pure hydrogen. The weak force enables stars to synthesize heavier elements like carbon, nitrogen, and oxygen, the essential ingredients for life. It also powers the slow, steady burn of stars, controlling how fusion unfolds over billions of years. The neutrinos produced by these reactions stream through space and through your body in unimaginable numbers every second. The weak force might seem subtle compared to gravity or electromagnetism, but it is the quiet engine of cosmic chemistry. Every atom in your body has passed through its influence, transformed by its invisible touch, somewhere in the history of the stars. It's the reason stars can burn slowly instead of exploding instantly. If the weak force did not exist, nuclear fusion would happen in a violent flash rather than a gentle glow. In the Sun, hydrogen atoms must undergo a weak interaction to fuse into helium, a process that takes immense time. Because of this, the Sun shines steadily for billions of years rather than burning out in seconds. The weak force acts like a cosmic regulator, allowing stars to live long enough for planets and life to form around them. This delicate balance is what makes the universe habitable. Too strong, and stars would vanish in violent bursts. Too weak, and they would never ignite. The steady light of the Sun is a testament to how precisely the forces of nature are tuned. The weak force is carried by particles heavier than entire atoms of iron. The weak nuclear force operates through massive particles called W and Z bosons. Each is about 90 times heavier than a proton, roughly the mass of an entire iron atom, confined to a single quantum of energy. Because they are so heavy, the weak force acts only at extremely short distances, less than 1,000th of a proton's width. These particles flicker into existence for the briefest instant during nuclear reactions, then vanish again. Their immense mass explains why the weak force seems feeble compared to electromagnetism or the strong force. In truth, it is not weak by nature, it is limited by the weight of its carriers. The discovery of these bosons in the early 1980s confirmed a major prediction of particle physics and helped unify our understanding of how the fundamental forces operate. Without it, the universe would be cold, dark, and chemically empty. If the weak force did not exist, neutrons could never turn into protons, or vice versa. The universe would be locked in a sterile state of hydrogen and nothing else. No helium, no carbon, no oxygen, no complex chemistry. Stars would never ignite, and planets could not form. The weak force drives the nuclear reactions that fill the periodic table and power the light of the cosmos. It is the hidden alchemist behind every element that makes life possible. Though invisible and short-ranged, its influence reaches from the hearts of stars to the atoms in your body. Every breath you take, every molecule that builds your cells, exists because the weak force gave matter the ability to change. Without it, creation itself would never have begun. Gravity on Earth shifts slightly every day as the planet's mass moves beneath us. Earth's gravity feels constant, but it's always changing. As magma flows beneath the crust, as glaciers melt, and as oceans rise and fall with the tides, the planet's mass redistributes. These movements subtly alter the gravitational pull in different regions. Satellites equipped with precision sensors can detect these tiny fluctuations, mapping the planet's hidden rhythms. Scientists use them to track ice loss at the poles, monitor groundwater reserves, and study how tectonic plates move. Even the weight of seasonal rainfall can be detected from space. Gravity, often thought of as steady and eternal, is in fact alive with motion, responding to the shifting balance of Earth itself. Every step you take rests on a field that changes as the planet breathes, a reminder that even the ground beneath your feet is part of a living, dynamic world. Gravitational lensing lets us see galaxies hidden behind others. Light always travels in straight lines, yet in the presence of gravity, those lines bend. When a massive object like a galaxy cluster lies between us and something more distant, its gravity warps the light from the background object, focusing it toward us like a gigantic lens made of space-time. Astronomers call this gravitational lensing, and it allows us to see galaxies that would otherwise be invisible. Sometimes the light forms glowing arcs or perfect rings, magnifying objects that existed when the universe was young. Through these cosmic lenses, telescopes can peer billions of years into the past, revealing the first generations of stars and galaxies. The distortions also expose the presence of dark matter, whose gravity bends light even though it emits none. Every lensed image is a photograph of space-time itself in motion, a natural telescope built by the universe's own architecture. Black holes can make light orbit them in perfect circles. Around every black hole lies a region called the photon sphere, where gravity is so intense that light can orbit the black hole in a perfect loop. Photons that travel endlessly around the darkness, neither escaping nor falling in. If you could stand safely at a distance and look toward this region, you would see distorted reflections of the universe wrapping around the black hole's edge, light trapped in eternal orbit. The boundary of the photon sphere marks one of the strangest thresholds in physics, where geometry itself curves so steeply that space behaves like a mirror. It is this region that creates the glowing rings seen in the first images of black holes captured by the Event Horizon telescope. The light you see in those images has circled the black hole many times, its path carved by the deepest gravity known to exist. The Milky Way's gravity warps light from galaxies billions of years away. Our galaxy is not only home to stars and planets, but also acts as a giant gravitational lens. Its combined mass bends the paths of photons that pass near it, slightly altering the apparent positions of galaxies behind it. For astronomers, this effect is both a challenge and a gift. It distorts the view of the distant universe, but also magnifies faint, ancient galaxies that would otherwise be too dim to detect. By studying these warps, scientists can measure the Milky Way's invisible dark matter halo, the vast envelope of unseen mass surrounding our galaxy. The effect is subtle but constant, proof that even here, gravity continues to sculpt light across unimaginable distances. Every star in the Milky Way participates in this cosmic act of refraction, shaping how we see the universe beyond our own home. Gravity binds the universe together, yet can never be blocked or shielded. Most forces can be stopped or deflected. Electromagnetic waves can be absorbed. Strong and weak forces act only within atoms, but gravity cannot be blocked by anything. It passes freely through matter, through planets, through your own body, unimpeded. This universality is what makes it so difficult to study and so powerful in shaping the cosmos. You can shield yourself from light with a wall, but there is no such thing as gravity-proof material. Every mass attracts every other, no matter how far apart they are. This endless reach is why gravity dominates at large scales. Over cosmic distances, all the other forces fade away, leaving gravity to sculpt galaxies, guide the motions of stars, and bind time and space into one continuous whole. It is the one force you cannot escape, woven into the fabric of existence itself. Space itself expands against gravity, and we don't yet know why. Gravity pulls everything together, yet the universe as a whole is expanding, and that expansion is speeding up. This mysterious acceleration is driven by something we call dark energy, a form of energy that seems to exist even in empty space. It pushes galaxies apart, stretching space-time faster than gravity can pull it back together. No one knows what dark energy truly is. It might be a property of the vacuum itself, or an undiscovered field filling the cosmos. What we do know is that it dominates the universe, making up about 70% of all its energy. The result is a grand cosmic tug-of-war, gravity pulling inward, dark energy pushing outward, both shaping the ultimate fate of everything. The stars you see tonight drift ever farther away, carried by a quiet expansion that began nearly 14 billion years ago and shows no sign of ending. Magnetic fields exist around every star, planet, and galaxy. Wherever there is motion of charged particles, magnetic fields arise. Every planet with a molten core, every star burning with plasma, every swirling galaxy generates its own magnetic presence. Earth's field protects us from solar radiation, guiding compass needles and shaping the auroras. The sun's magnetic field drives its cycles of flares and storms. Even in deep interstellar space, magnetic fields thread through the gas between the stars, influencing how new suns are born. These cosmic magnetic structures are often invisible but detectable through the way they polarize light. In galaxies, they spiral along with the stars, extending tens of thousands of light years. Magnetism, so familiar in everyday life, is also one of the universe's most far-reaching phenomena. It ties the smallest particles of plasma to the motion of galaxies, uniting scales that differ by trillions of times. Even empty space can carry magnetic energy. Magnetic fields do not require matter to exist. They can stretch across pure vacuum, independent of air or particles. When fields change, they create electric fields, and vice versa, maintaining their own presence even in what appears to be nothingness. In interstellar space, vast magnetic lines thread through the void, storing energy and guiding charged particles that wander through. During solar storms, these fields connect with Earth's, releasing bursts of radiation that can disrupt satellites and power grids. Magnetic energy fills the gaps between stars, shapes cosmic plasma, and influences how galaxies evolve. Even the smallest quantum fluctuations in empty space can generate magnetic effects. The vacuum is not empty at all. It is alive with invisible motion, humming quietly with fields that span the universe from one horizon to another. Every heartbeat creates a tiny magnetic field measurable from outside your body. With each beat of your heart, an electrical impulse travels through the muscle tissue, coordinating its contraction. This electrical activity produces a faint magnetic field that extends beyond your body. Sensitive instruments called magnetocardiograms can detect it several centimeters away. The field is weak, far weaker than Earth's, yet it carries the rhythm of life itself. The same principle applies to the brain. Neurons firing together create patterns of electrical current that can be detected as magnetic signals, allowing scientists to map thought and emotion. You are, in a very literal sense, a magnetic being. Every organ that relies on electricity, from the heart to the nerves, creates ripples in the surrounding electromagnetic field. These signals connect the physics of the cosmos to the physiology of life, proof that the laws shaping galaxies also hum softly within you. Solar flares are magnetic fields snapping open and releasing energy. The sun's surface is a boiling sea of plasma, threaded with magnetic lines that twist and tangle as the solar material churns. Sometimes these magnetic loops become so distorted that they suddenly break and reconnect, releasing vast amounts of energy in a violent burst known as a solar flare. In minutes, a flare can release as much energy as billions of nuclear bombs, sending streams of charged particles hurtling through space. When these particles reach Earth, they can disrupt satellites, damage power systems, and create dazzling auroras near the poles. Solar flares are a reminder that magnetism is not gentle but dynamic and explosive. It governs the behavior of stars, controls the flow of energy through the solar system, and links our fragile planet to the fiery heart of the sun. The auroras you see are powered by those same violent solar storms. When solar flares or coronal mass ejections hurl charged particles toward Earth, they follow the planet's magnetic field lines into the upper atmosphere near the poles. There they collide with oxygen and nitrogen atoms, transferring energy and causing them to glow. The result is the aurora borealis in the north and the aurora australis in the south, shimmering waves of light that dance across the sky. The colors and movement depend on which gases are struck and how intense the storm is. Sometimes the auroras reach far toward the equator, visible where they are rarely seen. What looks peaceful from the ground is actually the visible edge of a global electromagnetic storm. The lights are a reminder that Earth is not isolated, but connected to the restless power of its parent star. The strong force is carried by particles called gluons, nature's ultimate glue. Inside every proton and neutron, quarks are bound together by massless particles known as gluons. Their name fits perfectly because they act as the glue holding matter together at its deepest level. Gluons constantly exchange between quarks, maintaining a balance of color charge, the quantum property that governs the strong force. Unlike photons in electromagnetism, gluons interact with each other, weaving a dense web of connections that cannot be broken. If one quark moves, gluons instantly adjust, redistributing the energy. This network of forces confines quarks so completely that none have ever been observed alone. The gluons themselves create most of the mass of ordinary matter, not by their weight, but through the energy of their motion. Every atom, every star, and every living being owes its solidity to this invisible self-knitting web inside the nucleus. Quarks can never exist alone. The strong force instantly spawns more when separated. Try to pull quarks apart, and the strong force resists more fiercely the farther you go. Stretch the bond enough, and the energy becomes so great that it transforms into matter, creating a new quark-antiquark pair. Instead of isolating one particle, you end up with two bound systems. This is why quarks are never found in isolation. They exist only in groups, usually as threes inside protons and neutrons, or in pairs called mesons. This phenomenon, known as confinement, makes the strong force unique among all interactions. It ensures that the building blocks of matter remain forever connected. What seems like a limitation is also a gift. Without confinement, atoms would fall apart and the universe would have no stable form. The strong force is the unbreakable promise of matter, a law that keeps everything whole. A single proton contains more energy than the particles themselves contribute. When scientists probe the inside of a proton, they find that most of its mass does not come from the quarks that make it up, but from the energy of their motion and the gluons that bind them. The three quarks are almost weightless, yet they move at near light speed within the proton's tiny volume. Their kinetic energy, combined with the energy stored in the strong force field, accounts for nearly all the proton's mass. According to Einstein's equation, Energy and mass are interchangeable, and here that relationship is vividly real. The proton is not a static object, but a whirlpool of energy trapped by its own gravity and binding forces. Every atom in your body, every gram of matter you see, owes its existence to this restless internal storm. You are made of motion, condensed into permanence. Neutron stars are held up by the strong force fighting gravity to a standstill. When a massive star runs out of fuel, its core collapses under gravity's enormous pressure. Protons and electrons merge to form neutrons, and the strong nuclear force locks them together so tightly that the collapse halts. The result is a neutron star, a sphere only about 20 kilometers wide, but heavier than the Sun. A teaspoon of its material would weigh billions of tons. Inside, gravity pushes inward with unimaginable strength, but the strong force pushes back, keeping the star from collapsing into a black hole. The entire object is a balance between two extremes of nature, attraction and repulsion, frozen in perfect opposition. The surface of a neutron star glows with trapped radiation and intense magnetic fields, a remnant of the battle that defines the universe's most compact form of matter. Without it, every atom would explode from electrical repulsion. Inside the nucleus, protons all carry positive charge, and like charges repel each other. Without the strong nuclear force binding them together, that repulsion would tear the nucleus apart instantly. The strong force acts like cosmic glue, overpowering the electric push between protons at short range and keeping the nucleus intact. Even in heavy elements where dozens of protons crowd together, this force maintains balance, allowing atoms to exist in stable form. It is so powerful that it outweighs the electromagnetic repulsion by a factor of about 100. Yet it acts only across distances smaller than the size of a proton. This delicate balance between attraction and repulsion defines matter itself. Without it, everything solid would fly apart, leaving behind a featureless sea of charged particles. The weak force breaks the rules of symmetry, favoring one-handedness over another. Most physical laws treat left and right as identical, but the weak nuclear force does not. It interacts only with particles that spin in a particular direction, what physicists call left-handed particles. This strange asymmetry, discovered in the 1950s, shattered the long-held belief that nature always preserves mirror symmetry. The universe, it seems, has a preference. This bias shows up in radioactive decay and in the behavior of neutrinos, which are always left-handed. No one fully knows why the weak force discriminates in this way, but it has deep implications for the structure of reality. The tiny imbalance between left and right may be part of the reason matter exists at all, a fundamental twist built into the code of the cosmos. That tiny imbalance may explain why matter exists at all. In the earliest moments after the Big Bang, matter and antimatter were created in almost equal amounts. When they met, they annihilated, leaving behind pure energy. Yet somehow, a small excess of matter survived. Physicists suspect that the weak force's violation of symmetry played a role. During certain interactions, it treats matter and antimatter differently, allowing a minute fraction of matter to persist after most of the universe's pairs cancelled out. That sliver of imbalance became everything we see today: galaxies, stars, planets, and life itself. Without that slight preference, the universe would contain nothing but light. The fact that you exist at all may be the direct consequence of a subtle twist in the weak force, a tiny bias written into the earliest equations of creation. The weak force is the quiet sculptor of the universe's chemical diversity. While the strong and electromagnetic forces build the framework of matter, the weak force reshapes it. In the hearts of stars, it turns protons into neutrons and back again, determining which elements can form and in what abundance. It governs the rate of nuclear fusion and decides how long stars live. Without it, the universe would be frozen in hydrogen, unable to evolve. With it, stars become factories, forging new elements that later seed planets and life. The weak force operates silently, with no glow or flash, but its influence defines the chemistry of existence. Every atom heavier than hydrogen owes its existence to this quiet cosmic sculptor that allows matter to change form without losing its essence. Neutrinos created by the weak force stream through you by the trillions every second. Every second, tens of trillions of neutrinos pass through your body, through the walls, and out the other side, without a single collision. They are the most elusive particles in the universe, created by nuclear reactions in stars, supernova, and the Big Bang itself. Neutrinos interact only through the weak force, making them almost invisible to matter. Huge detectors buried deep underground wait for the rare event when a single neutrino strikes an atom. These ghostly visitors carry information from the cores of stars and the distant past of the cosmos. They prove that even the emptiest space is alive with motion and energy. At any given moment, countless messengers from across the universe are streaming through you, silent witnesses to the workings of the weak force. They almost never collide with anything, passing straight through solid rock. Neutrinos are so indifferent to matter that they can travel through entire planets as if nothing were there. Billions are produced by the sun every second, and most pass directly through Earth without interacting with a single atom. To detect them, scientists build massive tanks of water or ice, deep beneath mountains or under the sea, shielded from other types of radiation. Occasionally, a neutrino will strike an atom, producing a faint flash of light that reveals its presence. These events are rare but invaluable, offering glimpses into processes that no telescope can see. Neutrinos carry the story of the universe's most energetic events, from exploding stars to the birth of galaxies. They are the ultimate travelers, immune to barriers, moving effortlessly through worlds and stars alike. Gravity bends not only space, but time itself. Einstein's general theory of relativity changed everything we thought we knew about the universe. He showed that gravity is not a mysterious pull acting across empty space, but the result of mass and energy curving space-time itself. The curvature extends not only through the three dimensions of space, but also through time. Near a massive planet, clock ticks slow ever so slightly compared to clocks far away. On Earth, this effect is small but measurable, used every day to correct the timing of GPS satellites. Near a black hole, time nearly freezes. The deeper you go into a gravitational well, the slower time flows for you compared to someone far away. Gravity, then, is not simply about falling. It is about living in a universe where every second, every heartbeat and every sunrise flows differently, depending on where you stand in the great cosmic landscape of curved spacetime. In a black hole, time stops entirely from an outside perspective. Imagine watching a spacecraft fall toward a black hole. As it nears the event horizon, its signals stretch into slower and slower pulses of light. From your vantage point, those pulses never stop completely, but they take longer and longer to arrive, fading to red until they vanish. To you, the ship appears frozen on the edge of darkness. Time, for it seems to stop. But for the travelers aboard, time continues normally. They fall inward and cross the horizon in seconds, never noticing anything strange at all. This paradox lies at the heart of relativity. Time itself is not universal, but depends on perspective. Around black holes, this difference becomes absolute. From the outside, time halts. From within, it rushes forward toward a singularity where all paths end. The event horizon is not merely a boundary in space. It is the boundary of time itself. Einstein proved that gravity isn't a force, it's geometry. For centuries, gravity was understood through Newton's elegant law. Masses attract one another with a predictable pull. It worked beautifully, yet it implied that gravity acted instantaneously across the universe, faster than light, a mystery even Newton disliked. Einstein's insight was to replace the idea of force with geometry. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. Planets orbit stars not because they are being pulled, but because they are following the straightest possible paths called geodesics through curved space. Even light, which has no mass, bends around massive bodies because it follows that same curved geometry. The concept of a force disappears entirely, leaving only shape, warping, and flow. The sun does not reach out and tug Earth through emptiness. It simply bends space, and Earth glides along the curve like a marble rolling across a warped surface of reality. The Earth actually falls around the sun in curved space-time, not because it's pulled. To our intuition, it seems the sun pulls the Earth through invisible gravity. In truth, there is no pull at all. The sun's mass bends the space-time around it, creating a curved geometry that Earth simply follows. In this curved space, the straightest path is not a line but an orbit, a continuous fall that never ends because the ground beneath keeps curving away. This motion is effortless, like floating within a whirlpool of geometry. Even the Moon's orbit around Earth follows this same rule. Every planet, asteroid, and comet dances through warped spacetime, not through force, but through natural motion. Remove the sun, and space would flatten instantly. The Earth would stop curving and drift off in a straight trajectory forever. This understanding turned gravity from a mysterious attraction into a precise, beautiful expression of how space itself behaves in the presence of matter and energy. Every planet follows the shape of spacetime carved by its star. A star's mass does more than create light. It sculpts the fabric of reality around it. The geometry it forms becomes the stage on which planets move. Each planet's orbit is not an arbitrary path, but a direct reflection of that curvature. The closer a planet is, the deeper it sits in the star's gravitational well, moving faster to balance the bend of space-time beneath it. Farther out, the curvature flattens and motion slows. This balance creates harmony throughout solar systems, an invisible architecture of motion. Even the tilt of an orbit or the wobble of a planet can reveal the unseen shape of spacetime around its star. From the tiniest moon to entire galaxies, everything follows these natural curves, not through effort, but through inevitability. Gravity's beauty lies in this order. Every orbit is a graceful response to the shape of reality itself. The electromagnetic spectrum spans from radio waves to deadly gamma rays. Light is far more than what our eyes can see. It exists as a continuous spectrum of electromagnetic waves that vary only in wavelength and energy. At one end are long, slow radio waves stretching for kilometers, carrying communication and cosmic whispers. Next come microwaves, used to heat food and map the weather. Infrared radiation reveals warmth. Visible light paints our world in color. Ultraviolet rays carry invisible energy that can burn skin. X-rays pass through flesh to reveal bone. And gamma rays born from supernova and black holes hold enough power to alter atomic structures. All are expressions of the same force, oscillations of electric and magnetic fields moving through space at the speed of light. The electromagnetic spectrum is vast and unbroken, a cosmic rainbow that tells the story of everything radiant, energetic, and alive across the universe. Wi-Fi, sunlight, X-rays and microwaves are all the same phenomenon, just at different frequencies. Every form of electromagnetic radiation, from the faintest radio signal to the fiercest burst of gamma rays, is the same thing vibrating at different speeds. Frequency determines behavior. Long, slow waves transmit wireless signals and radar. Faster ones make up visible light and heat. Beyond that, high-frequency waves such as X-rays and gamma rays carry immense energy capable of splitting molecules and altering DNA. Yet they all travel at the same speed, the speed of light. The differences that define them come only from how quickly their electric and magnetic fields oscillate. The glow of a sunset, the pulse of a Wi-Fi router, and the radiation from distant stars are all manifestations of one unified phenomenon. That unity means the universe speaks one electromagnetic language, from your phone to the most ancient galaxies, all communicating through the same rhythmic vibration of light. A changing magnetic field can create electricity, and electricity can create magnetism. Electricity and magnetism are two sides of the same physical coin. When electric charges move, they generate magnetic fields. When magnetic fields change, they create electric currents. This interplay, discovered by Faraday and later described by Maxwell, forms the foundation of nearly all modern technology. Power plants use rotating magnets to generate electricity. Electric motors reverse the process, turning electric current back into motion. The two are linked so perfectly that you cannot have one without the other. Even light itself is an electromagnetic wave, a self-sustaining ripple of electric and magnetic fields creating each other as they move. Every time you flip a switch, charge a battery, or feel the warmth of sunlight, you are witnessing this endless feedback loop. It is one of the most elegant self-perpetuating relationships in nature, transforming invisible motion into the energy that powers our world. That feedback loop powers every generator on Earth. Every watt of electricity that lights our cities or powers your devices is born from motion through magnetic fields. In a generator, coils of wire spin within magnets, or magnets spin within coils, creating a constantly changing magnetic environment. This change induces electric current, converting kinetic energy into electrical energy with extraordinary efficiency. Whether driven by steam turbines, waterfalls, or wind, the principle remains the same. The magnetic field is invisible, yet it acts as the bridge between motion and light, between the physical and the electrical. From the vast spinning turbines of hydroelectric dams to the tiny alternators in your car, this elegant loop sustains modern civilization. It connects the physics of the stars, where electromagnetic induction rules plasma motion, to the physics of our homes. Humanity's entire technological heartbeat flows through this beautiful interaction discovered nearly 2 centuries ago. Superconductors expel magnetic fields completely, making magnets float in mid-air. When some materials are cooled to near absolute zero, they enter a remarkable state where electrical resistance vanishes entirely. In this superconducting state, they also repel magnetic fields completely, forcing them to stay outside the material. This effect, known as the Meissner effect, can make a magnet levitate above a superconductor, locked in place by invisible magnetic tension. The current inside the superconductor flows forever without losing energy, a perfect electrical loop that could, in theory, last for eternity. This discovery opened doors to magnetic levitation trains, quantum computers, and powerful particle accelerators. It also hints at the perfection hidden in nature's laws, where matter and magnetism cooperate in frictionless harmony. A floating magnet is more than a laboratory curiosity. It is a glimpse into a world of pure physics, where energy moves endlessly, effortlessly, and silently. The strong force holds nuclei together, but can also tear them apart in fusion or fission. The strong nuclear force is nature's most powerful interaction. Inside every atomic nucleus, it binds protons and neutrons so tightly that separating them requires unimaginable energy. Yet under extreme conditions, that same force can release energy instead of consuming it. When light nuclei combine in fusion, as in the Sun, the resulting nucleus is slightly more stable, and the leftover energy emerges as light and heat. When heavy nuclei split in fission, energy is also released because the fragments are more tightly bound. Both processes, fusion and fission, tap into the balance of the strong force, converting mass into energy through Einstein's equation. This is the power that fuels the stars, drives the most energetic explosions in the universe, and illuminates our world. The strong force gives matter its strength, yet it also holds the secret to its transformation. It's responsible for the Sun's power and nuclear energy on Earth. Deep in the Sun's heart, temperatures exceed 15 million degrees Celsius. At those conditions, hydrogen nuclei move so fast that they overcome their natural repulsion and fuse together. The strong nuclear force binds them into helium, releasing immense energy that radiates outward as light and warmth. That same principle governs nuclear reactions on Earth, where we harness it through both destructive and peaceful means. In power plants, splitting heavy atoms like uranium releases energy stored in the strong force's bonds. In laboratories, scientists work to replicate fusion itself, hoping to create a clean, near-limitless power source. The sunlight on your skin and the hum of a reactor both trace their lineage to the same fundamental interaction. The strong force converting matter into radiant energy, sustaining life across the solar system. It acts only at subatomic distances, smaller than a trillionth of a meter. The strong force is mighty but fleeting. It operates over distances smaller than a trillionth of a meter, less than the diameter of a proton. Beyond that range, it disappears almost completely. This short reach is what keeps the universe stable. If it acted farther, matter would fuse uncontrollably, collapsing everything into dense nuclear clusters. Within its tiny realm, however, the strong force dominates, overwhelming even the fierce repulsion between protons. It binds quarks into protons and neutrons, and those nucleons into atomic nuclei. This delicate balance defines the structure of matter. The range of the strong force marks the boundary between chemistry and nuclear physics, between the world of molecules and the furnace of stars. It is a reminder that even the smallest distances can hold the universe's greatest powers. Gluons themselves carry color charge, making the force self-interacting and chaotic. The strong force is carried by particles called gluons, which bind quarks together inside protons and neutrons. Unlike photons, which do not interact with one another, gluons carry the same kind of charge they exchange, called color charge. This makes the strong force uniquely self-referential. Inside the nucleus, gluons constantly split and merge, forming a storm of energy that never rests. This interaction grows stronger the farther quarks move apart, preventing them from ever existing alone. The equations that describe this process, known as quantum chromodynamics, are so complex that supercomputers are required to model even tiny systems. Yet this chaos produces stability. Out of the wild energy within each proton arises the calm solidity of matter. The gluons' relentless self-interaction gives rise to almost all the mass of the visible universe. The weak force helps stars forge elements like carbon and oxygen. The weak nuclear force might seem humble next to gravity or the strong force, but it is the quiet craftsman behind the elements of life. It allows particles to change identity, turning protons into neutrons and vice versa, enabling the chain reactions inside stars to continue. Without it, fusion would stop at helium, and the periodic table would end there. Thanks to the weak force, stars can fuse heavier elements like carbon, nitrogen, and oxygen, the essential ingredients for biology. In dying stars, the weak force also drives supernova explosions, scattering those elements into space. Every breath of oxygen you take and every carbon atom in your body owes its existence to these transformations. The weak force may act only on the smallest scales, but its influence stretches across galaxies, building the diversity of matter itself. Without it, you wouldn't exist. Your body's atoms depend on weak interactions. If the weak force vanished, the universe would be stillborn. Hydrogen would remain hydrogen forever, unable to fuse into heavier elements. The stars would never ignite, and the cosmos would be cold and chemically barren. The weak force enables radioactive decay, beta processes, and the slow transmutation of elements that fill the universe with complexity. It is the reason unstable isotopes become stable, and why carbon, oxygen, and iron exist at all. Even now, traces of weak interactions warm Earth's interior, powering volcanic activity and helping sustain our planet's magnetic field. Though invisible and seemingly delicate, the weak force is life's hidden architect. Every atom in your body was once shaped by its quiet hand, inside a star that lived and died long before the sun was born. You exist because the universe learned how to change. Gravity shapes galaxies, while electromagnetism makes them shine. Gravity gives the universe its form. It draws matter together into stars, then binds those stars into galaxies. But gravity alone would make a dark, cold cosmos. It is electromagnetism that brings light and motion. The energy released from fusion in stars is carried outward by electromagnetic radiation, illuminating the universe. Magnetic fields throw through galaxies, influencing the flow of plasma, guiding star formation, and shaping jets of energy that stream for light years into space. These two forces, working together, create the grand cosmic architecture we observe. Gravity sculpts, electromagnetism animates. Without one, the other would be meaningless. The Milky Way's glow across the night sky is the visible harmony between them, a portrait of how attraction and light coexist to create beauty on the largest possible scale. The strong and weak forces build every nucleus inside those stars. Within the hearts of stars, two invisible forces work together to build the universe. The strong nuclear force binds protons and neutrons into stable nuclei, while the weak force allows them to transform, enabling the chain reactions that forge new elements. Every atom heavier than hydrogen, every particle that makes up your body, your planet, and the air you breathe was created through this partnership. The balance between them determines a star's lifespan and its ultimate fate, whether it fades gently into a white dwarf or explodes in a brilliant supernova. On the smallest scales, these forces decide how atoms behave. On the largest, they decide how galaxies evolve. From the center of a star to the chemistry of your cells, the strong and weak forces quietly weave the fabric of existence, one nucleus at a time. All four forces together define the structure of reality. Everything that exists, every star, every cell, every heartbeat, is the result of four fundamental forces acting in concert. Gravity binds the cosmos on vast scales, gathering matter into stars and galaxies. Electromagnetism shapes atoms, creates light, and drives chemistry. The strong nuclear force holds atomic nuclei together, while the weak force allows them to change, creating new elements. Together, these four forces build all structure, all motion, and all experience. Each one dominates its own realm, yet they depend on one another in perfect balance. If even one were slightly different, the universe would collapse, burn, or fail to form at all. Every breath you take, every star you see, is a fleeting harmony among these four notes in nature's grand symphony. Gravity is 1,000 billion 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 times weaker than the strong force. It sounds impossible that something so weak could rule the universe. The gravitational attraction between two protons is so small that it is utterly dwarfed by the strong force that binds them. Quantitatively, gravity is about 1,000 billion 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 times weaker. Yet because it always attracts and never cancels, its influence grows with size. Stars, planets, and galaxies are massive enough for gravity's collective pull to overcome all others. That weakness is also a gift. It allows stable orbits, gentle tides, and long cosmic lifetimes. Were gravity even slightly stronger, stars would burn out in moments. Weaker, and galaxies would never form. The universe we know depends on this improbable balance, the mightiest structures shaped by the gentlest of all forces. Yet gravity rules the universe because it always attracts and never cancels out. Gravity is the weakest of the four forces, yet it dominates the structure of everything large. While electromagnetism can both attract and repel, cancelling out across atoms and molecules, gravity only attracts. Every particle of matter in the universe adds its pull to every other, creating a force that strengthens as mass accumulates. A planet's gravity is the sum of countless tiny pulls working in unison. Stars and galaxies owe their formation to this one-sided nature. Gravity binds cosmic dust into planets, stars into galaxies, and galaxies into clusters. Over billions of years, it turns chaos into structure, giving the universe shape. Even light bends under its influence, curving around stars and black holes. What it lacks in power, it makes up for in persistence. Gravity never turns off, never repels, and never forgets. Its patience is what rules the cosmos. The photon is massless, which is why light can travel forever. Photons are the carriers of the electromagnetic force, tiny packets of light energy with no mass at all. Because they are massless, they never slow down. From the instant of their creation, they move at the cosmic speed limit, the speed of light. A photon emitted from a distant galaxy can cross billions of light years without losing pace or needing energy to keep going. It may scatter, shift color, or be absorbed by an atom, but it never slows. Its timeless journey connects every point in space. The light from ancient stars reaching your eyes tonight began before Earth even formed. Inside that light is a record of the universe's history, preserved perfectly across unimaginable distances. Photons are not just the messengers of energy, they are the universe's memory, racing endlessly through the vacuum, carrying whispers from the dawn of time. The W and Z bosons are heavy, which is why the weak force acts over tiny distances. The weak nuclear force governs radioactive decay and the transformation of particles inside stars. Yet it operates over an incredibly small range. The reason lies in the mass of its force carriers, the W and Z bosons. Unlike photons, which are massless, these bosons are massive about 90 times heavier than a proton. Because of that mass, their exchange between particles requires enormous energy, confining their influence to the subatomic realm. They flicker into existence for only the briefest instant before decaying. This is why the weak force affects only processes like beta decay and fusion inside stellar cores. Despite its short reach, it shapes the universe profoundly, allowing matter to change and stars to shine steadily. Without the W and Z bosons, there would be no slow burning of stars, no creation of heavier elements, and no stable universe at all. The gluon and photon have no mass, giving them unlimited range within their fields. Two of the four fundamental forces, electromagnetism and the strong nuclear force, are carried by massless particles. The photon carries electromagnetic energy, while the gluon carries the strong interaction that binds quarks together. Because they have no mass, they can travel at the speed of light and reach across any distance within their fields. The photon's influence extends infinitely, fading with distance but never truly disappearing. The gluon, although massless, behaves differently. It cannot escape the confines of atomic nuclei because the strong force grows stronger with distance, trapping gluons and quarks together. Both particles define the behavior of their respective realms. Photons give light its endless freedom, spreading across the universe, while gluons give matter its solidity, locked forever in microscopic storms of energy. Together, they reveal a universe where massless particles are the true architects of structure and motion. Scientists have united electromagnetism and the weak force into one, the electro-weak interaction. For decades, physicists believed that electricity, magnetism, and the weak nuclear force were separate phenomena. But as experiments probed higher energies, evidence emerged that they share a common origin. This unification became known as the electro-weak theory, one of the greatest triumphs of modern physics. At extremely high temperatures like those that existed just after the Big Bang, the electromagnetic and weak forces become indistinguishable, behaving as a single, unified interaction. Only as the universe cooled did they split, creating the two forces we observe today. This discovery, confirmed through experiments involving the W and Z bosons, showed that nature's apparent complexity hides deep simplicity. The electroweak theory was a milestone, a stepping stone toward the grand dream of uniting all four forces into one elegant framework. Beneath the variety of physical laws lies a single voice of symmetry. At high energy, they become indistinguishable, merging into a single unified force. When physicists recreate the extreme conditions of the early universe inside particle accelerators, the boundaries between forces begin to blur. At energies far beyond what we experience daily, the electromagnetic and weak forces merge into one, described by the same mathematical equations. This happens because the particles that carry them, the photon, W and Z bosons, behave identically at high energy, losing their differences. In those moments, nature reveals its original simplicity, when the universe was young and hot enough that all forces were one. Understanding this state is key to unlocking the next level of unification. If electromagnetism and the weak force merge under these conditions, perhaps gravity and the strong force once did too. To study high energy is to look backward in time, toward a universe where division did not yet exist. In the early universe, all four forces were one. At the beginning of time, the universe was unimaginably hot and dense. In that first fraction of a second after the Big Bang, the four fundamental forces did not yet exist as separate entities. Gravity, electromagnetism, the strong force, and the weak force were merged into a single, unified interaction. Only as the universe expanded and cooled did this perfect symmetry break apart. The first to separate was gravity, followed by the strong force, and finally the electroweak interaction split into the weak and electromagnetic forces. These cosmic phase transitions defined everything that followed. They determined how matter formed, how energy flowed, and how galaxies would eventually emerge. The four forces we know today are fossils of a once unified law. To understand that lost unity is to glimpse the original blueprint of reality. As the cosmos cooled, They split apart in a process called symmetry breaking. The early universe was filled with perfect symmetry. Every force, every particle, every law behaved as part of one harmonious whole. But as the temperature dropped, that symmetry became unstable. Like ice forming from water, the universe underwent phase transitions, and the unified forces fractured into distinct identities. This process, called symmetry breaking, is the reason gravity, electromagnetism, and the nuclear forces behave differently today. With each break, new particles appeared, and the properties of matter emerged. What had been smooth and uniform became structured and diverse. Symmetry breaking is one of the most important ideas in physics because it explains how complexity arises from simplicity. The universe we live in is not the original, pristine version, but the cooled, crystallized aftermath of a perfect symmetry that shattered in beautiful order. The Higgs field gives particles their mass, allowing the weak force to exist at all. Throughout the vacuum of space lies an invisible energy field known as the Higgs field. As particles move through it, some interact strongly and slow down, gaining mass, while others pass freely and remain light. The particles that carry the weak force, the W and Z bosons, gain their enormous mass this way. Without the Higgs field, they would move at light speed, and the weak force would disappear entirely. The discovery of the Higgs boson in 2012 confirmed this idea, showing that the field is real. The Higgs mechanism is what allows the diversity of matter, from electrons to protons, to exist as tangible, massive things. It is the reason particles can clump into atoms and atoms into worlds. Without it, the universe would remain a ghostly sea of light, never able to take form. Without the Higgs mechanism, matter would move at light speed, unable to clump together. If the Higgs field did not exist, the universe would be a strange and lonely place. All fundamental particles would be massless, zipping through space at the speed of light, never slowing down, never binding into atoms or molecules. There would be no stars, no planets, no life-only endless streams of radiation racing through the void. The Higgs field provides the drag that turns light-like motion into substance. By interacting with this field, particles gain inertia and begin to behave like matter instead of pure energy. Every object you see, from the smallest grain of dust to the largest galaxy, owes its existence to this invisible ocean of energy. The Higgs mechanism did not just give the universe mass. It gave it structure, stability, and the possibility of permanence in a world that could have been nothing but light. Gravity has no known particle. The hypothetical graviton has never been found. In quantum theory, every force has a carrier particle. Photons for electromagnetism, gluons for the strong force, and W and Z bosons for the weak. Gravity, however, remains the exception. The particle that would carry gravitational interactions is called the graviton, a hypothetical quantum of space-time curvature. If it exists, it would be massless and travel at the speed of light, like the photon. Yet no experiment has ever detected one. Gravity is so weak on small scales that single gravitons would be nearly impossible to observe directly. Their effects are drowned out by quantum noise. Still, their existence fits beautifully into the framework of quantum field theory. Finding the graviton, or proving how gravity operates at the quantum level, remains one of the greatest unsolved mysteries in science, missing piece of the universe's deepest equation. If it exists, it would be massless and travel at light speed, like the photon. The graviton, if real, would be a massless particle carrying the quantum imprint of gravity. Like photons, it would move at the speed of light, transmitting the curvature of spacetime in discrete packets. Unlike photons, however, its effects would be unimaginably subtle, noticeable only when dealing with enormous masses or cosmic distances. Detecting one would require a sensitivity far beyond our current technology. Instead, we observe gravity's ripples indirectly through gravitational waves, space-time vibrations caused by violent cosmic events, such as colliding black holes. These waves behave exactly as a swarm of gravitons would, lending weight to the idea that they exist. If proven, it would unify gravity with the other forces at the quantum level, finally closing one of the most profound gaps in our understanding of nature. Some theories suggest gravity might emerge from deeper quantum information laws. What if gravity is not fundamental at all? Some physicists believe it may arise from the way information is organized in quantum systems. According to this idea, space and time themselves emerge from patterns of entanglement, the invisible links that connect particles across the universe. Gravity would then be a side effect of how information flows and rearranges itself. The geometry of space-time might be a kind of hologram, encoding deeper quantum rules underneath. This radical view turns gravity from a primary force into an emergent phenomenon, like temperature arising from molecular motion. The idea could explain why gravity resists unification with quantum mechanics. It is not a separate force, but a collective behavior of something deeper. If true, it would mean that space, time, and gravity are all illusions woven from the hidden logic of quantum information. Others think extra dimensions could explain why it is so weak. Some physicists suspect that gravity's weakness is not a flaw, but a clue. It may seem weak because part of it leaks into hidden dimensions beyond the three we experience. In certain models of string theory, the universe contains additional spatial dimensions curled up so tightly that we cannot perceive them. The other forces are confined to our familiar dimensions, but gravity spreads into the whole multidimensional fabric, diluting its strength. This idea could explain why it is so much weaker than the other forces, and why it behaves differently at large scales. Experiments at particle accelerators and precise measurements of gravity at microscopic distances continue to search for evidence of these hidden dimensions. If found, they would reveal a universe far richer and stranger than anything we have imagined our cosmos, with unseen directions where gravity quietly escapes. The Sun's core is a balance between gravity's inward pull and fusion's outward push. At the heart of the Sun, two colossal forces are locked in perfect balance. Gravity pulls inward, trying to collapse the star under its own weight. At the same time, nuclear fusion releases energy outward, pushing back with equal strength. This equilibrium keeps the Sun stable, neither expanding nor imploding. If gravity was slightly stronger, the Sun would shrink, heating up until it burned out quickly. If fusion was stronger, it would expand and cool, dimming over time. The delicate balance between inward pull and outward pressure defines a star's life. Every ray of sunlight on Earth is the visible result of this harmony. The Sun's calm surface hides an eternal struggle beneath a dance of attraction and release that has kept our world warm for billions of years. Every star is that same tug-of-war, made visible as light. Every star in the universe, from tiny red dwarfs to immense supergiants, exists because of a constant battle between two opposing powers. Gravity works to compress the star's matter inward, while the energy from nuclear fusion pushes outward. This cosmic tension reaches equilibrium, and the result is light. The brightness of a star is the visible signature of balance. When gravity wins, the star collapses into a white dwarf, neutron star, or black hole. When fusion dominates, the star expands into a giant before fading away. The entire life cycle of stars, from birth to death, is governed by this struggle. What we see as serenity in the night sky is, in truth, a dynamic standoff, an eternal compromise between the deepest pull of matter and the burning will of energy. Black holes form when gravity wins completely. In some stars, the balance between gravity and fusion does not last forever. When the nuclear fuel runs out, nothing remains to push back. Gravity crushes the core inward with unstoppable strength. If the mass is large enough, even the pressure from neutrons cannot resist, and the collapse continues until space-time folds in on itself. The result is a black hole, a region so dense that not even light can escape its pull. Its boundary, the event horizon, marks the edge of the observable universe for anything caught inside. Beyond that, the laws of physics as we know them cease to apply. Black holes are not cosmic monsters but natural consequences of gravity's persistence. They are reminders that, in the end, geometry can trap light itself and turn space into shadow. White dwarfs exist where quantum pressure barely holds gravity back. When a star like our Sun exhausts its fuel, it sheds its outer layers and leaves behind a dense coral white dwarf. In these tiny remnants, gravity tries to compress the star further, but quantum mechanics intervenes. The electrons inside resist being squeezed into the same state, creating what is known as electron degeneracy pressure. This quantum pressure halts the collapse, balancing gravity in a delicate stalemate. A white dwarf packs the mass of the Sun into a sphere no larger than Earth, glowing faintly as it slowly cools over billions of years. If it gains too much extra mass, gravity will overcome that pressure, triggering either a supernova or collapse into a neutron star. White dwarfs are the quiet embers of the cosmos, proof that even after death, stars can linger in fragile equilibrium. Neutron stars balance the strong force and gravity at the edge of collapse. When a massive star explodes in a supernova, its core may compress beyond the white dwarf stage into a neutron star. In this state, protons and electrons combine into neutrons, forming an object of unimaginable density. A teaspoon of neutron star material would weigh billions of tons. Gravity pushes inward with overwhelming force, but the strong nuclear interaction between neutrons resists compression. This balance forms one of the most extreme objects in the universe. The surface gravity is so powerful that mountains can rise no higher than a few millimeters. Some neutron stars spin hundreds of times per second, emitting beams of radiation that sweep across space like lighthouses. These pulsars are cosmic reminders of how the fundamental forces meet at the limits of physics, creating stability out of near-impossible conditions. In a supernova, all four forces clash together in a single, violent instant. A supernova marks the death of a massive star, but it is also a moment of extraordinary creation. Inside, gravity collapses the core inward, while the strong and weak forces reshape atomic matter at unimaginable speed. Electromagnetism carries away the resulting burst of energy as light, radiation, and expanding shock waves. In seconds, all four fundamental forces act together, releasing more energy than the Sun will emit in its entire lifetime. This explosion forges heady elements like gold, silver, and uranium, scattering them through space to seed new worlds. Supernovae are both endings and beginnings. They demonstrate the raw power of the forces that govern everything, from the smallest atom to the largest galaxy. In their brilliance, the universe remembers how to begin again. The electromagnetic force repels, but the strong force resists separation with infinite stubbornness. The electromagnetic force is familiar to us because we live inside its domain. It allows atoms to form, magnets to pull, and lightning to flash across the sky. It can both attract and repel, balancing positive and negative charges in endless motion. The strong nuclear force, however, is different. It binds the very heart of matter and refuses to let go. Inside the nucleus, protons should repel one another violently, their identical charges pushing them apart. Yet they remain locked together because the strong force overwhelms electromagnetism by an almost unimaginable margin. It grows stronger the farther particles try to separate, as if the universe itself resists division. When scientists attempt to pull quarks apart inside particle accelerators, the effort only creates new particles rather than freeing them. The strong force does not merely bind matter. It enforces unity, ensuring that the fabric of the universe remains indivisible. A single magnet contains trillions of aligned atomic spins acting in perfect coordination. Magnets appear almost magical, but their power comes from perfect order among countless atoms. Every electron spins, and this spin gives it a tiny magnetic moment, a small invisible arrow of magnetism. In most materials, these arrows point in random directions and cancel one another out. In a magnet, however, vast regions of atoms align in unison, their spins pointing the same way. The result is a field strong enough to move objects at a distance and store information within metals. Trillions upon trillions of atomic spins act as one, producing a collective magnetic presence that reaches beyond the object itself. This order arises naturally in certain materials when cooled or placed within a strong magnetic environment. The magnet you hold in your hand is a quiet miracle of cooperation. It is matter at its most disciplined, showing how unity at the smallest scale can create power at the largest. The magnetic field of a pulsar can strip electrons from atoms thousands of kilometers away. A pulsar is one of the most extreme creations of the universe. Formed after a massive star collapses, it squeezes more mass than the Sun into a sphere only about 20 kilometers wide. Its rotation is astonishing, sometimes hundreds of times per second, and its magnetic field is almost beyond comprehension, 1,000 trillion times stronger than Earth's. Such power can rip electrons from atoms, ionizing matter across vast distances. Near a pulsar, space becomes a storm of radiation, magnetic lines twisting like ropes of fire. As it spins, a pulsar emits focused beams of energy that sweep through space with clockwork precision. When those beams cross our planet, they appear as rhythmic pulses of radio light, more accurate than any human-built clock. Pulsars are proof that magnetism can shape not just materials, but the very behavior of space-time itself, turning gravity's leftovers into spinning engines of cosmic order. Lightning bolts contain enough energy to power an entire city for seconds. A single bolt of lightning releases more energy in a moment than most people can imagine. Within a thundercloud, rising warm air and falling rain separate electric charges until the voltage between them becomes unbearable. When the air finally breaks down, a massive current surges through the sky. Temperatures rise to around 30,000 degrees Celsius, hotter than the surface of the sun, and the air expands explosively, creating thunder. That brilliant flash of plasma carries enough electricity to power a city for several seconds, but it lasts less than a heartbeat. Lightning travels both upward and downward, connecting cloud to ground through a rapidly branching path of ionized air. It is a pure expression of electromagnetism in motion, one that bridges the heavens and earth. Every flash you see is a reminder that the same laws governing galaxies also rule the storm clouds above our heads. Every electric current generates a magnetic field that curls around it. Whenever an electric current flows, it shapes the space around it. Moving charges generate a magnetic field that spirals around their path in perfectly predictable circles. This discovery, first made by Hans Christian Ørsted in 1820, revealed the unity between electricity and magnetism. The direction of the field depends on the direction of the current, forming invisible loops that expand and contract as the current changes. This principle powers everything from electric motors to wireless communication. Even the tiny currents inside your brain create faint magnetic fields that can be measured with delicate instruments. On a planetary scale, molten iron flowing in Earth's core generates the magnetic field that protects us from solar radiation. From the subatomic to the cosmic, every movement of charge writes invisible geometry into space. Magnetism is not separate from electricity, it is its shadow, curling beautifully around the flow of energy itself. Even the single moving electron reshapes space around it instantly. An electron in motion is not just a point darting through space, it is an event that changes the structure of reality around it. As it moves, it drags an electromagnetic field that stretches outward in every direction. That field defines how nearby particles behave, guiding forces and interactions. In quantum theory, this influence is even stranger. The electron is surrounded by a haze of virtual particles that constantly appear and vanish, subtly modifying its field. When the electron accelerates, it emits ripples of electromagnetic energy that can travel across the universe. Every flicker of electricity, every pulse of light begins with the motion of electrons. Though unimaginably small, they continuously sculpt the invisible texture of the world. Each moving electron is like a pebble dropped into a still pond, sending endless ripples across the fabric of space and time. The strong force is mediated by 8 types of gluons, each carrying color charge combinations. The strong nuclear force operates through particles called gluons, which bind quarks together inside protons and neutrons. There are 8 distinct kinds of gluons, each carrying a combination of color charges red, green, and blue along with their opposites. These colors are not literal but mathematical labels that describe how quarks interact. The gluons constantly exchange between quarks, stitching them together in a dynamic web of energy. Because gluons themselves carry color charge, they can interact with each other, creating an endlessly shifting storm inside every atomic nucleus. This complexity makes the equations of quantum chromodynamics, the theory that describes the strong force, among the hardest in all physics. Yet this turbulent chaos produces perfect stability. The interplay of 8 massless gluons ensures that matter remains whole, transforming raw quantum energy into the solid, dependable substance of the universe itself. Gluons have no mass, yet they create nearly all the mass of visible matter through energy. It might seem paradoxical that the particles responsible for the strong force are massless, yet the energy they generate accounts for almost all the mass in the visible universe. Inside a proton or neutron, quarks are held together by a constant exchange of gluons. These gluons create a sea of energy so dense that it outweighs the quarks themselves by 1,000-fold. According to Einstein's equation, energy and mass are interchangeable, meaning the energy of the strong interaction literally becomes the mass of the proton. When you hold a rock, a cup, or even your own hand, you are feeling the weight of confined energy, the tension of countless gluons locked in perpetual motion. The solidity of the world is not from particles, but from energy trapped within them, forever swirling, forever binding, forever giving substance to what we call matter. The weak force governs radioactive decay, the heartbeat of unstable atoms. Deep within certain atomic nuclei, change is constant. Neutrons can transform into protons and vice versa, emitting tiny particles called electrons and neutrinos in the process. This transformation is made possible by the weak nuclear force. Though it acts over distances smaller than a single proton, it plays a crucial role in the evolution of matter. The weak force drives radioactive decay, determining how long isotopes remain stable and how elements gradually change over time. The warmth of Earth's interior, the glow of distant stars, and the age of the oldest rocks all depend on this subtle interaction. Without it, stars would not shine steadily, and no new elements would form. The weak force's quiet influence gives the universe rhythm. Its invisible hand guides the slow transformation of matter, marking time on scales far longer than any human life. Radioactivity warms Earth's interior and powers its magnetic field over billions of years. Far beneath Earth's surface, the slow decay of radioactive elements has been generating heat for billions of years. Uranium, thorium, and potassium atoms deep within the mantle and core emit particles through weak force interactions, releasing energy as they transform into lighter elements. This heat keeps the planet's interior molten, driving convection currents in the outer core that generate Earth's magnetic field. The movement of that molten metal acts like a giant dynamo, creating a protective shield that deflects harmful solar radiation and cosmic rays. Without radioactivity, the planet would have cooled long ago, its magnetic field gone, its surface cold and static. Volcanoes, earthquakes, and the slow drift of continents are all powered by this same atomic heartbeat. The weak force, though nearly invisible, sustains the living world by keeping the planet's core alive and the sky above us safe. Gravity sculpts space-time, but quantum mechanics says space-time itself fluctuates. Einstein's general relativity paints space-time as a smooth, continuous surface that curves around massive bodies. Yet quantum theory reveals a far stranger truth. On the tiniest scales, space and time are not smooth at all, but frothing with energy. Particles and antiparticles appear and vanish constantly, creating tiny ripples in geometry itself. This quantum foam means that space-time may fluctuate endlessly, changing its structure from moment to moment. If we could shrink ourselves to the Planck scale, distances would blur, time would shimmer, and nothing would remain stable. Gravity, at that level, may not even exist as a distinct force, but as a statistical effect emerging from this quantum chaos. The universe we experience the smooth, predictable oneies, an averaged version of something wildly alive beneath it. Reality, at its root, might be an ocean of uncertainty from which all structure emerges. Physicists are searching for a quantum theory of gravity that unites the large and the small. Modern physics rests on two pillars: general relativity, which explains gravity and the large-scale universe, and quantum mechanics, which governs the world of particles. Both are incredibly successful, yet they are fundamentally incompatible. Relativity describes a smooth space-time continuum. Quantum mechanics describes probabilities and uncertainty. Reconciling them into one unified theory has become one of science's greatest quests. Candidates like string theory and loop quantum gravity propose that space-time might be made of vibrating strings or discrete loops of quantum information. Experiments searching for tiny distortions in gravitational waves or subtle quantum effects in black holes could hold the answers. A true quantum theory of gravity would not only unite physics, but also reveal what happened in the first instant after the Big Bang. It would be the ultimate bridge between the cosmos and the atom, between everything large and everything small. Gravitational waves pass through you constantly, stretching space without you feeling a thing. Every second, ripples in space-time wash across your body, stretching and squeezing the distance between your atoms by unimaginably tiny amounts. These are gravitational waves, created when massive objects such as black holes or neutron stars collide. Predicted by Einstein and first detected in 2015, they confirmed that space itself can vibrate like a fabric. Though they carry immense energy, their effects are so faint that only the most precise instruments can detect them changes smaller than 1 part in 1,000 trillion trillion. Each passing wave is a message from distant cosmic events, a faint whisper from places we will never see. The Earth, the Sun, and even your heartbeat move gently with these waves, united in a rhythm older than time. You do not feel it, but you are forever dancing to the gravitational music of the universe. Magnetars, ultramagnetized neutron stars, could erase your credit card from half a galaxy away. A magnetar is what remains when the core of a massive star collapses and its magnetic field intensifies beyond comprehension. With fields 1,000 trillion times stronger than Earth's, a magnetar can twist atoms, bend light, and even distort the structure of nearby space. A single magnetar could destroy electronics from vast distances, and up close, it would shred matter at the atomic level. Occasionally, these stars unleash flares of gamma radiation that outshine entire galaxies for a brief moment. Their crusts crack under the strain of their own magnetism, releasing bursts of energy powerful enough to alter the spin of the star itself. Only a handful are known, yet they demonstrate how extreme nature's forces can become. A magnetar is the universe's most magnetic objector celestial reminder that even after death, a star can still command unimaginable power. The weak force lets the sun transmute hydrogen into helium-1 particle at a time. At the heart of the sun, temperatures and pressures are so high that hydrogen atoms collide with enough energy to fuse. Yet without the weak force, even those conditions would not be enough. It allows a proton to transform into a neutron, enabling two hydrogen nuclei to bond and form deuterium, the first step in the chain that builds helium. This reaction releases vast amounts of energy that travel outward as light and heat, sustaining the solar system. The weak force's role is subtle, but without it, stars would never ignite. Each reaction happens on a timescale of billions of years per atom, yet together, they create the brilliance of the sun. The faint glow that warms your skin is powered by countless tiny weak force transformations unfolding continuously in the depths of a distant star. Fusion in your body's atoms once began in that same weak interaction inside stars. Every atom in your body carries the memory of a star. The carbon in your cells, the oxygen in your blood, and the calcium in your bones were all forged in stellar cores through nuclear fusion. The weak force made this possible by allowing hydrogen to fuse into heavier elements. When those stars reached the end of their lives, they exploded, scattering their enriched material into space. Over billions of years, that dust and gas coalesced into new systems, one of which became the Earth. Every breath you take, every movement you make, depends on atoms born in ancient suns. The weak force does not just power stars, it connects you to them. It is the quiet thread linking every living thing to the furnace of creation, proof that the matter of life and the matter of stars are one and the same. The strong force prevents the universe from being pure radiation, giving matter substance. Without the strong nuclear force, quarks would never bind together, and protons and neutrons would not exist. The universe would be nothing but a flood of light and energy, expanding endlessly with no form or structure. The strong force changes that. It traps energy within particles, converting radiation into matter, giving the universe weight and texture. It is the bridge between the intangible and the tangible, the reason the cosmos feels solid beneath our touch. Its influence determines how stars burn, how atoms form, and how elements combine. Every stone, tree, and living being exists because the strong force transforms chaos into structure. It is nature's act of creation repeated endlessly across space, turning waves of energy into the architecture of existence itself. Gravity ensures that substance clumps, forms stars, and becomes worlds. Once matter exists, gravity takes control. Its slow, patient pull gathers dust and gas into clouds, clouds into stars, and stars into galaxies. Over time, it sculpts the universe into the magnificent structures we see today. Without gravity, the strong force would produce matter, but that matter would drift forever, never forming planets or people. Gravity shapes possibility into form, pressing matter until fusion ignites and light is born. It creates order from chaos, not through violence, but through steady persistence. From collapsing nebulae to orbiting moons, every movement of the cosmos follows its rhythm. Gravity turns existence into architecture, transforming the potential created by the other forces into something you can see, touch, and live within. Together, the four forces create everything that exists, from galaxies to thought. Gravity, electromagnetism, the strong force, and the weak force are the four keys to the universe. Each one plays a distinct melody, yet together they form the cosmic symphony that makes existence possible. Gravity gathers matter, electromagnetism builds atoms and carries light. The strong force binds the nucleus, and the weak force transforms elements inside stars. Change any one of them, even slightly, and everything would unravel. There would be no stars, no chemistry, no life. The entire universe depends on their perfect balance. Every heartbeat, every distant galaxy, every spark of intelligence is written in their equations. They are not separate laws, but different verses of one vast poem, sung continuously by the fabric of reality. Everything that exists is an echo of their harmony. The universe is not made of things. It is made of forces endlessly at play. When you look deep enough into matter, you find that there are no solid objects, only relationships between forces. Particles are temporary ripples in invisible fields, sustained by interactions that never stop. The four fundamental forces are the verbs of existence, the ceaseless actions that create and recreate reality every moment. Atoms hold together because of exchange, stars shine because of balance, and life endures because those balances continue without fail. The universe is not static, it is movement frozen in patterns, energy shaped by the tension of forces. Every mountain, every ocean, every living cell is a slow ripple in that motion. To understand the universe is to understand that it is not built but performed, an ongoing dance of gravity, electromagnetism, and the nuclear forces playing without pause since the dawn of time. And now, as the currents of the universe grow quiet again, you can rest in the calm that follows wonder. The forces that shape reality never sleep yet. Somehow, they lull us into peace. Gravity keeps your body close to the Earth, a quiet tether to the planet's slow heartbeat. Electromagnetism hums softly through the air, carrying the warmth of light that touches your skin. Even the strong and weak forces are at work within you, keeping your atoms whole, your body alive, your world intact. Everything around you, every sound, every breath, every thought exists because of balance. The same equilibrium that holds the stars in their orbits also holds your heart in its steady rhythm. You are not separate from the universe. You are an expression of it, a pattern of forces made conscious for a brief and beautiful moment. Somewhere, distant galaxies drift apart in silence. Stars are born, live, and die in the same cosmic music that moves through you. Every moment is part of that rhythm. Every heartbeat echoes a law written long before life began. You are made of stardust, bound by gravity, illuminated by electromagnetism, sustained by nuclear fire. You are, in every sense, made of the same story the universe tells itself. So let your thoughts unwind. Let them fall like dust through starlight. Feel the weight of gravity as a comfort, the pulse of light as a lullaby, the stillness between breaths as a doorway to sleep. The cosmos continues its endless motion, vast, beautiful, and utterly at peace with itself. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too. One sleepy soul at a time. For now, just breathe. Let your eyes grow heavy, and let the forces of the universe cradle your thoughts slow, weightless, and free. Good night.